Today we'll be doing 7.5 exponential growth and decay. At the end of this lesson, you will be able to use properties of exponents to transform expressions for exponential functions. If you think back to earlier in the unit, we talked about the growth and decay functions. So here are the formula for those functions. Growth, f of t equals a times the quantity 1 plus r raised to the t. Decay is f of t equals a times 1 minus r raised to the t, where a is greater than or equal to 0 and t is greater than 0. Don't forget the way you identify the variables is a is your initial amount or your initial population, the amount you start with, the population you start with. R is the rate of increase or decrease. Make sure that you convert the percent to a decimal, move it over 2 spots. So 5% would convert to 0.05, 15% would convert to 0.15. Do not forget to convert the percent to a decimal. And t represents the time you are looking at. Be aware of the units. It could be months, it could be years, it could be quarterly, bi-weekly. So look at that, take that into account. So our first example, a city has a population of 10,000 people. It is growing at a rate of 2%. What will the population be in 10 years? So let's identify our variables. A, our initial amount or our initial population is 10,000. R, the rate. The rate is growing at 2%, which is going to convert to 0.02 when I move the decimal 2 spots. And what will the population be in 10 years? So t is 10. Seeing how this is a growth population, we need to plug it into the formula f of t, the function. When we plug in time equals a times 1 plus r raised to the t. So I rewrite it, f of t is going to equal 10,000 times the quantity 1 plus our rate 0.02 raised to the t. That's the function that we would use. So we can simplify that to 10,000 times 1.02 raised to the t. Now we can plug in any time we want and figure out the future population. The future population we want is 10 years. So f of t is going to equal f of 10, because we are finding 10 years. So we are plugging 10 in for t. Remember, the 10 is the exponent on the 1.02. It does not affect the 10,000. So now I plug it into my calculator just as I wrote it. 10,000. Parentheses, 1.02, parentheses, the caret to raise it into the exponent, 10. And I get the function after 10 years for population, it's going to be 12,189.9442. I want to round that up because I can't have a fraction of a person, so I'm going to make this 12,190 people. Always round up, even if it's a number less than 5. You want to account for that extra little bit and round it up. Example 2, a city has a population of 14,000 people. It is decreasing at a rate of 13%. What will the population be in 10 years? So our initial population is once again the A, so 14,000 people. Our rate is 13%, which converts to 0.13, and we're going to find the population in 10 years, so T is 10. It says the population is decreasing, so now we're going to use the decay formula. So F of T is going to equal 14,000, our initial population, times the quantity 1 minus 0.13, subtraction because it is a decay, raised to the t power. I'm just writing the function now. So 14,000 times, simplify 1 minus 0.13, 0.87, raised to the t. So we can plug in any time we want for future populations. Put the population we want, f of t, but instead of t we want to plug in 10 years, so f of 10 is going to equal 14,000 times 0.87 raised to the 10th power. The 10 only affects the 0.87, not the 14,000. Plug it into the calculator just as I wrote it, so 14,000 parentheses 0.87 parentheses raised to the 10th power. I get f of 10, so after 10 years, when the population is decreasing at 13%, after 10 years there will be 3,477.928 people. I can't have a fraction of a person, so I'm going to round up. 3,478 people. Example 3. Two towns have populations modeled by the function f of x equals 6,000 times 0.6 to the t, and g of x equals 15,000 times 0.4 to the t, where time starts in the year 2013. 2013 is our 0 year, so we need to be careful now whenever we start doing our future populations. Example A says, what is the population of each town in the year 2013? Well, 2013 is our 0 year, so we look at the initial population. The initial population of f of x is A, which is 6,000 people. The initial population of G, which is the A for G of x, which is 15,000. So G of x is 15,000 people. The other way you could check would be to plug in 0 for t, and anything to the 0 power is 1, so 0.6 to the 0 would be 1, leaving us 6,000 people. 0.4 to the 0 is 1, leaving us 15,000 people. Example B says, in the year 2015, which town has more people? So now we're looking at 2015, which if 2013 was 0, that would now mean that time is 2 years later, so t equals 2. So we need to plug that into both functions. So f of 2 is going to be 6,000 times 0.6 raised to the 2nd power. Plug it into the calculator just as I wrote it, 6,000 parentheses 0.6 parentheses, use the caret, raise it to the 2nd power. So in the year 2015, which is 2 years later, the population is 2,160 people. And I do G of 2 for the g of x function. So g of 2 is 15,000 times 0.4 raised to the second power. Plug it into the calculator just like I wrote it. 15,000 parentheses 0.4 raised to the second power. So g of 2 is 2,400 people. Both of them are decays because the rate 0.6 and 0.4 are both less than 1. So that's why I now have 2,160 people and 2,400 people. So the example asks for which town has more people. G of 2 has more people. So the town represented by the function g of x is the one with the highest population. So now for the year 2018, 2018 would be 5 years after 2013. So t equals 5. So now we're going to plug 5 into f and g. So f of 5 and then we're going to do g of 5 plug both of these into my calculator. So f of 5, I get the population is 466.56. So I'm going to round that up to 467 people. G of 5 plug that into the calculator. Get 153.6. Round that up to 154 people. So the example asks which town has more people. This time it is the f function, 467. So the last thing we need to do with this is our exponential regression. This is using the calculator to find the equation, just like we did with linear regression. So there are the steps to entering in your calculator. On the next example, I'm going to use this to find the regression equation. But now instead of it being linear, we are going to have an exponential equation. Alright, so here's a table. It shows the number of internet hosts from 2000 to 2006. So 2000 is our 0 year, with initial population of 120. And then it increases as the years go on. What you'll notice is when you do this exponential regression, even though it shows an initial population or initial amount of 120, that may change whenever we put it into the calculator. So don't count on your 0 year ending up your initial population. So I'm going to show you how to do this on the calculator. So I'm using my TI I'm going to first go to stat. I'm going to enter in my lists. So the X values will go into L1, the Y values into L2, or my years starting at 0 into L1, and then the number of internet hosts into L2. So L1, 0 through 6. L2, corresponding Y value. So 120, 183, 185, 240, 324, 405, 499. My lists match up. I have equal amounts in both lists, so I entered everything in correctly. So now I hit stat, and I want to calc. The exponential regression. L1 and L2 is where I want it, but now I need to store the regression equation. That's where you hit vars over to y vars, and we want it to go in y1 so that it'll store it in our equation y equals. Hit enter, and there's our regression equation. Y equals AB to the x power. A is 126.411729. B, the rate at which it's changing, 1.257904941. And then our correlation coefficient R. So now that I have my variables from the exponential regression, A, my initial population, I'm going to round to 126.41. B, the rate at which it's changing, 1.26. So I know this is a growth because it's greater than 1, which makes sense because the number of hosts is going up every year, and a correlation coefficient of 0.98, which if you think back to linear regression, that means this is very close. It's almost 99% accurate. So my equation, or my function f of t, function as a relation of time, is going to be 126.4 times 1.26 raised to the t power. Just asked me to find the population, or the number of internet hosts in 2009 and 2013. So 2009, t is going to be 9 because it's 9 years after 2000. 2013, t is going to equal 13 because it's 13 years after 2000. So f of 9, 126.4 times 1.26 raised to the 9th power. Plug that into the calculator. 126.4 times 1.26 raised to the 9th power. I get, when t equals 9, for the year 2009, there will be 1,011 11.77 internet hosts. So I'm going to round that to 1,012 internet hosts. Then I'm going to plug 13 in to predict the amount of internet hosts in 2013. So F of 13 is 126.4 times 1.26 raised to the 13th. Plug that in. So F of 13 is 2,550.14. Round that up. So in 2013, I'm predicting there will be 2,551 internet hosts. Make sure you guys bring your calculators tomorrow so you can practice this on the worksheet.